Yeah, so recording has started. So I will follow certain style, or that is what I have been following from the last semester, and that sort of turned out to be reasonably effective. So we will follow the same style in this part of my whatever I am going to teach in Mass Transfer 2 as well. So as you all know, I sort of like interacting classes. I never like monologues. So first thing, let me assure that I am not going to show you some PPTs or read out stuff from the PPTs. That's, in my opinion, the worst form of teaching that can happen, and that's the most boring one. So we will try to replicate a blackboard with some sort of a improvised whiteboard, which is, and I'm not very tech savvy. I'm not very comfortable with this software, Microsoft Teams, though it has a lot of features as Microsoft claims. So I'm going to use a PPT, a blank PPT slide, and a writing tab I have. With that, I'm going to write. So first thing is, I'd like to request all of you exactly the way when I take a real class, and you sit with a pen and your notebook, and you copy whatever I'm writing on the board, or discussing on the board, or take running notes based on whatever discussion. Kindly try to replicate that instead of just sitting back, relaxing. And I also know winter morning, so some of you are joining from under your blankets. So it's time you actually get up and wake up. Sit with a pen and paper. Don't remain with that comfort zone that there is some advantage of being online. Of course, many of you have network issues. I do appreciate that. But some also are very happy that recording to anyway we will get the recording and notes and this and that, so that I'm going to catch up later. That never happens. You can never sort of replace a real class experience, and I'll try to make it as interactive as possible. Second thing is that if you remember your CPC lectures, I do throw some questions, and I expect the people in the class to respond. That somehow I feel that most of the students or most of the batches sort of enjoy. So what we are going to do is we are going to replicate that in a slightly different way. Of course, we do understand that if you give answers over here, microphones can be an issue, there can be echo, there can be noise. So what we do is we will follow the, or we will mute all our microphones. So all the microphones will be muted except my microphone. Please do not turn it on, even if you have a doubt or if you want to ask a question. Instead of that, please use the chat box. So I will use the chat box. We will rather use the chat box very efficiently, right? So all the doubts to be asked in the chat box, because I will not go to the way I will use my PPT, the chat box will remain visible to you. So for all of you, I do understand those of you who are joining from phones, who accessing the chat box might be slightly difficult, but try to place your questions, your answers, and if you understand that your comments. So I many times would be asking, is it clear? And give an honest opinion if it is not clear, because if you do not give me any feedback, I will assume that I am teaching to a bunch of super brilliants, or I'm teaching some real great stuff in a cool way, and I will never repeat. And in the process, if you recall my regular classes, the way we sort of build concepts is based on a fair deal of exchange. I tell something, it might be acceptable or understandable to some of you, may not be fully understandable to some of you, and then we repeat in different ways. I typically try to give the same concept from different perspectives, and collectively we build a very good conversation, very good concept. So let us try to do that here also. So before I share my screen, so let me get ready with the stuff. So here is the chat box that we are going to use. Right. And what we do is So there we go. So is the screen visible to all of you? Answer replying to the chat box. That's perfect. Right, great. And good morning, everyone, and good to see all of you back. All known faces and known names, right? And a little bit too long, 11 days belated Happy New Year to all of you. And great to have all of you back in my classes again. And I'm joining from my office, so which is your most favorite place. What you realize, that's your department. What you realize since you are now away for the last 10 months. So the course is Mass Transfer 2. And what we also know that what I am assuming or not assuming, it is a fact that I am essentially teaching to a set of students who have already done a course on mass transfer. And therefore, the baseline would be, I will assume, and the assumption is correct, distillation is known to all. And let me assure you, my handwriting is slightly better in the tab. So since I'm teaching for the first time from my office, earlier last semester I was taking all the classes from my home. So it needs a little bit of time to get used to the table and all that. So we will try to make it as good as possible. So I'm assuming distillation is known to all of you, and you also understand what is diffusion, right? So with this much amount of background, we will learn a lot of things. We will discuss certain relevant things. So in my part, the operations, the mass transfer operations that we are going to cover is liquid-liquid extraction. Number 2 is leaching. And number 3 is adsorption. Right? And individual details, what is there in each of the chapters, I will not read out now. So extraction forms a major part of this particular course or this particular module, right? And we will see what are the things we are going to study as a part of extraction. Honestly, if I write down what are the stuff we are going to study today itself, it's not going to make any sense to you. So I will, what I will do is, we will sort of get started with extraction or discussion on extraction right away, and then pick up or gather some interest. We will try to find out what is extraction. It's a very simple technique. We will take not more than 5 to 7 minutes in understanding what is extraction, and we will start building our concepts straight away. And once we have developed some concept, then it will be far easier for all of you to understand what are the different types or different complex situations or simplified situations that you can encounter in extraction. And the textbook that I will be following is the very classic book, is Strebel's, nothing more fancy. And about the assessment, I will also wait for what is the institute's instructions on that. So maybe we will have 1 or 2 class tests or whatever, which might be multiple choice. And this part, I think the mid-semester or end semester or whatever the major examination, I think we will go for a pen and paper test, and I will ask the students to upload the responses after scanning. So that also we will discuss and decide a little later. So what is extraction? The method is the liquid-liquid extraction, as it is called. And it's a technique to separate two miscible liquids. Right? So how do you separate these two miscible liquids? Let me tell it straight away, and then immediately what we will do is we will come back and start comparing it or contrasting it with distillation, because when I say it's a method or technique to separate two miscible liquids, it should immediately ring to the mind of most of you is distillation also does the same thing. So why on earth we are again talking about a method which is going to separate two miscible liquids? And you will soon find that there is some additional problem in this particular technique that we are going to talk about. So how does the method or technique look like? The technique looks like you have a feed solution. Which is essentially a solution of two liquids. What are the liquids? You have one liquid which is called the solute, which is the important component. Sorry. Extraction has some typical notations, so we will follow that. And C is dissolved in A, which is another liquid, which is called the carrier. So C and A are completely miscible. So you have a feed which comprises of C and A. And then what you introduce is a solvent. We will draw a better picture. Solvent B. And so essentially your separation, your extraction unit can be a simple drum where you pour all these liquids. So you introduce the feed and you introduce the solvent B. And what is the unique nature of the solvent? C, well, the unique nature we will learn again in detail. That C is miscible in B and A is completely immiscible in B. So can you imagine what is going to happen here inside this chamber? Yes? Anyone? No microphones, please, chat box. It's a two-phase liquid, Harshal, right? So essentially, what will happen, there will be two phases of this liquid. Orientation. One is B plus C, and the other one will be A plus C, right? One is the B plus C. So, which is the solvent-rich phase, and this is, you can say the solvent lean, or there can be, it is sort of carrier rich, you can say. So this particular phase, this solvent rich phase, I'm coming back. I'm just describing what it is. I will revisit it again and again. This is called the extract, and this is called the raffinate, right? So obviously, what are the things you can say the only conclusion if you are running a successful extraction process? What is the only conclusion you can say from basic mass balance? The basic mass, from basic mass balance, what you can say, the fraction of C in the raffinate is going to be lower than the fraction of C in the feed. Is that clear to all? Is it clear to all? So let us redraw the whole system again. So this is a simple single stage extraction unit. And what you have is a feed. Comprising of A plus C. You introduce also a solvent, which is B. So when I say feed, feed actually comprises of solute and carrier, right? And here, so again, what are the unique properties we have? The solvent, or let me put it this way. The solute is miscible in the solvent, and the carrier is not miscible. When I say not miscible, this is a theoretical conjecture. Under real situation, there might be some very low amount of miscibility will be there, right? So after you have mixed it properly or thoroughly, you are likely to get, you will get two liquid phases, right? Which are, what is the interrelation between these two phases? These two phases are in equilibrium. I forgot to assume that I'm also teaching to a class who have a basic idea about equilibrium, right? So you end up getting two liquid phases. So one will be B plus C, right? And maybe trace of A under realistic situations. And the other will be A plus C plus trace of B. There can be a lot of discussion why this trace of A and trace of B comes in, but we will talk about it later. So this is the solute rich phase. Drawing a vertical straight line is a big problem this time. So this is called the extract, and this is called the raffinate, right? So this is so what is your product here? What is your product? Others also, not Ujjwal alone. The product is extract. And if you recall, or if you are listening to me carefully, so those of you who are sort of writing extract, it's perfectly fine. But if you sort of listen to me carefully, a few minutes back I told, number one, extraction is a technique which we use to separate two liquids, which distillation also does. But then on the go, I mentioned that extraction has its own share of problem. And what is the problem you can see? The problem is, it should be visible to all of you or understandable to all of you, that you would like to separate out C. Maybe C is some desired chemical. I can take the chemical names and give real life examples, but I will refrain to do that, refrain from doing it, because we are not learning chemistry. Of course, it's very important what is a system which can be extracted with what are the relative solubilities, but maybe we will talk about those things later. So if C is your product, right? The problem in this case, is the problem visible to all? What exactly is the problem I am referring to? Even after this successful extraction, there are a lot of advantages also, but there are some problems. What is the problem? Anyone? Are you getting my point? No one? The problem is your product is not pure C. Right? Anshuman. It is in solution with B. So your product is not a pure product. Eshan, trace A is not that great a problem. Impurities, partly it is true. But the biggest problem is, Ananya, don't give an answer like B, it doesn't make any sense. The biggest problem is you don't get a pure product. You get a product, solubility and miscibility, which will maybe after 2 classes, not right now. Give me some time. In principle, both are same, but I'll have to really think. Miscibility, I mean, see, I probably would say as of now, these are interchangeably used as of now. But solubility is a quantifiable parameter because you know from your basic chemistry about solubility product and this and that. So miscible, immiscible is more of a pedagogic term or more of common English to sort of talk about low and high solubility. I will place it like that right at this moment. But it's a very good point. I have never thought about this question. Nobody asked it to me before. So I will check about it and try to come up with a more rigorous or convincing answer if necessary. So the most important observation over here is that your product is not a pure product. And needs to be sort of, or there is a need for subsequent additional processing. Despite that, yes, Madhuri, in most cases, the product will be the extract because that is how the pedagogy is defined. C, which is the phase that is miscible in both A and B, right? So the way you introduce, right, as if C is mixed with A, okay? And then you are, so I was about to come to that. So what exactly is happening here? How is it similar to distillation? How it is different from distillation? So let's have a look. In distillation, you are essentially separating the two components based on the difference between their boiling points, right? So you are essentially supplying heat. So in order to separate, you have to supply some energy, particularly if the two phases are missing, right? So you are supplying energy, and then as you heat them up, right? So as you heat them up, the one with lower boiling point starts to vaporize first, and then somehow you have mechanism. All of you know about the distillation column. You have some mechanism to separate out. In fact, there can be lots of very interesting questions one can ask. Why do you go for fractionation? Why do you go for multiple stages? Why don't you do it all at one go, etc., etc.? I will address, in fact, some of those. In fact, one of my very favorite concepts is what exactly is the physical significance of the operating line. I'm coming to it. Right. So essentially, you separate the two based on their thermal properties or their essentially the boiling point. Right. Now, what you are doing here, is there any similarity? So the energy here is replaced with the solvent, right? You do not apply any energy. So most important thing is extraction is an isothermal process. So whatever is the temperature. Now again, there are a lot of questions and discussions one may ask. Should you do your extraction at room temperature? Should you do it at lower temperature than room temperature? Should you do it at a higher temperature? Normally, under industrial condition, extraction is performed at room temperature. Certainly not at elevated temperature, but we will talk about whether elevated temperature is required in certain cases or not. And so what exactly is the role of the solvent? The solvent sort of, if you mix the solvent sort of pulls out C, right? Remember of your childhood days, when you were engrossed playing with your friends, it's late evening, you have not returned home, and suddenly you find your mom is showing up, and she simply grabs you by your neck and pulls you out from the crowd of your friends to take you home so that you have your evening snacks and study. This incident, all of you remember? The role of the solvent is exactly the same. So C was having fun with A, right? And then B comes in, and B picks up the C molecules, right, into B. And then you now have more amount of C in B rather than with A. Of course, there are several questions again. How do you separate these two liquids, right? You have, even after this mixing, right, you will be having a B-rich phase and a C-rich phase. A B-rich phase and an A-rich phase. So in order to have a effective separation, right, you somehow need to separate these two out. And it is often also desired that there is a significant level of density difference between A and B, so that after these two, as all of you have said, mentioned that two-phase liquids, two liquid phases, one is a B-rich phase and one is an A-rich phase that will form, right? But you understand, most of you understand that this two-phase liquid can also remain in a dispersed phase. And if you have a dispersion, right, it is going to be very, very difficult to separate those two out. Not even we are talking about the level 2 separation between B and C from the extract. We are just talking about separating out the A-rich phase and the B-rich phase in the extractor itself. So, however, in contrast to that, if let's say in the extractor unit itself, after your things are allowed to settle down, right, and there is a stratification, again writing wrong, then you can easily separate them out. And what you may also want to recall or understand straight away, that whether, unlike a distillation column where your top product is always the lighter boiling component, lighter boiling material or component, here whether your top product is going to be the raffinate or the extract, or the bottom product is going to be the extract or the raffinate, entirely depends on the relative densities of A and B. And therefore, depending on if whatever is the, whichever between A and B has higher density, right? Depending on that, your extract or the raffinate can be the bottom product and vice versa. Is it conceptually clear to all of you? If there is any doubt, please feel free to stop me. There are a lot of things. I have not almost talked about anything now. but is it conceptually clear? And then, as I asked you, please give a feedback. So if you have understood whatever we have told, just write a yes, no, whatever. And if you have some genuine doubt, feel free to write it down in the chat box. The last part, okay, I'm coming to it, Ujjwal. Anything else? So in a nutshell, let me repeat again. And you all know that I teach very slowly, at least in the initial classes, we will go very slowly so that all of you understand. Why room temperature? Again, we will talk. Yeah. See, if you can do something at room temperature, right, isn't it the best option instead of wasting energy either in heating or cooling it up? Distillation does not work at room temperature. Therefore, so it might be fun for you. Why chooses B over A? Yeah, so of course, Arvind, you have to pick up. So there is something called, I was about to come to it. Good question. These questions, well, yeah, so Ujjwal, I'm coming to it one at a time, please. This question, I was about to ask, in fact. So how many of you know the concept of partition coefficient? So I will pick up Arvind's question. It's a very, very good question. Question he has asked is, if C is miscible in both A and B, why does it choose B over A? Simple answer. You must choose B in such a way. I will come to the formal part of it. You must choose B in such a way so that C has higher solubility in B than in A. Of course, even if C has lower solubility in B, but has some solubility, still some amount of C will leave A and go to B rich phase. Please understand this very carefully. This is a very, very interesting question, which actually would have come as a part of our discussion anyway, but I'm glad this question is being asked. So is the question clear to all? So the question is, if C is miscible in both A and B, right, why B is chosen over A? Well, I will not go back. I will give an answer to this. The first point is, typically you would like to choose your solvent in such a way. What is solvent? Solvent is the B. You'd like to choose your solvent in such a way so that the solute has better solubility in the solvent as compared to the carrier. So Arvind, does it make sense? This is what you typically like to choose. Does it make sense? However, please look into one important aspect. The important aspect is this. What is the definition of extract? The definition, Madhuri was also asking this question. So the definition of extract is not depending on whether the concentration of C in the extract is higher or lower. This is very, very important. So definition of extract is the solvent rich phase. So whichever phase has higher solvent, that is extract. Right? Importantly, there is no distinction. Please note this down. This is very important because there are certain problems where this confusion crops up. There is no distinction between extract and raffinate based on the composition or the relative composition, I would say, of C in the two. Okay. So if this sentence is clear, it would also mean that if you now are compelled to use a solvent which has poor solubility. You are under certain conditions compelled to use a solvent which has poorer solubility of C as compared to that in A, right? You will still have, since it has some solubility, some amount of some amount of C will still leave A and go into the B phase. Is that clear? So even it may so happen that amongst your extract and raffinate, the composition of C might still be, or the mole fraction of C might still be higher in the raffinate as compared to the extract. It is possible, it happens. There are situations, there are systems where this happens. However, what you need to understand is even if that happens, right, your composition of C in the raffinate is going to be lower than that in the feed. Is that clear to all? So what it means that though inefficient, the solvent has been able to extract out some C from the feed. It might be a very, very costly pharmaceutical drug, right? And even if an inefficient separation is better, again, the age-old concept of what I taught all of you in CPC, that the basic understanding of an engineer is something is better than nothing, right? So yes, let's say raffinate has more C. When we process raffinate, then no, Eshan, no. So see, you need to understand, if you are now in a position to process the raffinate, which is primarily A plus C, you could have done the processing of the feed itself. Why you bring in B, have some lower value of C in the raffinate, and then go try to process it? So one question actually is unanswered, and we have just gone into the next level, is why at all we do extraction. So Eshan, is your question clear? Is the point clear? So if you are in a position to process the raffinate, no need to be sorry. It's a very, very valid point. If you are in a position to do some other processing of the raffinate to take out C from A, you would have very well done that in the feed itself, isn't it? So there must be some problem why you can't do it, right? And therefore you have to, so it may so happen that by other separation techniques, the separation of A and C is not possible, right? And I'm coming to it. What makes it not possible? Most of you will understand, or most of you should understand when distillation fails, right? However, A and B separation might be possible, let's say by distillation only, right? So, B and C separation might be possible, let's say by distillation only, right? So even inefficient, even if C has lower solubility in B, you'd still like to take some C into B and then subject it to subsequent processing. Before I take more questions, let me ask a simple question now. This method looks simple on paper, it's complicated to execute. There is secondary processing of separation between B and C, but why do you think this process might be necessary? It might be necessary because you are again talking about separation of two liquids, right? So you know what is the most significant, most important, or most widely used method for separating two liquids? It's distillation. So this might be important in areas or places where distillation fails, right? And what are the what can be a situation where distillation fails? Yeah, now the class should answer. Very close, similar BP, or vapor pressures are same boiling point. That's it. Yeah, when the difference in boiling point is not much, low difference in boiling point, all are correct answers. There can be another situation where you cannot do distillation. And that is if you have, yeah, Madhuri, I was about to come. Don't say it might damage the liquids, but there can be some components which are sensitive to temperature. So you cannot really apply high temperature. But then I would say that you can do something else. I don't know whether you know that in a real petroleum plant, there are always two types of distillation units. The ADU, the atmospheric distillation unit, right, and the VDU, the vacuum distillation unit. Now, why do you use the vacuum distillation unit at all? And which column operates? So all of you know about the existence of ADU and VDU. This all of you know? Yes or no? Quickly. Very good. So, Shubham, your answer is absolutely correct. But the class knows the about the existence, because sometimes this is also covered in a petrochemical type of a course. So typically in a petroleum, the crude separating unit where you apply distillation, fractionating towers, there are typically two units, ADU and VDU, right? So as you apply a vacuum distillation unit, you all know that with increase or reduction in pressure, the boiling points goes down with the suppression of boiling point. And therefore, if it is temperature sensitive, then you can in fact go for a vacuum distillation, reduced pressure distillation, and you can try to have a separation at a lower temperature. But in cases, so this their boiling points are very close to each other or similar to each other, it becomes impossible to have distillation working successfully. So one classic example, let me just read out, must be having in my notes somewhere, is this, or in Chabel's book, I think I saw it yesterday, and I was preparing. I did not write down this names. So essentially is these chemicals or organic chemicals which have different type of orientations like ortho and meta and all these. So if their molecular weights are close to each other, I will give the example. That is the name of the chemical. Missing out where I have written it. It's very nicely written in Chabel's book. Sometimes it really helps to read books because you sort of feel excited, right? So if the molecular weights, and in organic materials this is possible, so the molecular weights are close to each other and the structures are different, then as you know that the boiling point to a large extent depends on the molecular weight also. For a chemical species, the chemical formula is going to be exactly same. In those type of cases where the boiling points are very close to each other, you rely on extraction. So I think up to this point, it is mostly clear with all of you. Can you explain, Shubhraja? So it is not exactly under the purview of this course, what is ADU and VDU. So go to the best educator, the Wikipedia. ADU stands for atmospheric distillation unit. And this stands for vacuum distillation unit. So those of you who are interested, may please check out what they are. Typically, you first run through the ADU, and then the bottoms or the whatever product you get from the reboiler, that you take to the VDU, so that you can separate them out. There are certain other aspects also which I may touch upon, though it is not exactly related to extraction. And you take them to VDU, you reduce the pressure and try to separate them further, right? So this is what is ADU and VDU. So there can be so some notes I had made. Applications where extraction and UU compared to other techniques, separation is not possible using other methods. Extraction. So the other important thing is like distillation and evaporation. You get direct separation. These are direct separation techniques. So you have pure products coming in, but in extraction there is a mixed state, and it has to be separated further. So water, acetic acid system, blah, blah, blah. Okay. So Madhuri, coming to your point, if you read tribbles, none of them are my own concept. So this is a very classical subject. So of course I have made the notes from tribbles, and what a teacher does is to make you understand stuff, because reading a book and understanding it is difficult and boring. So if you listen to it, it might appear to be simple. So Madhuri, coming to your point, what you mentioned that things can degrade under temperature, please also remember certain things might degrade also under vacuum. So there can be chemicals which cannot be subject to either high temperature or vacuum, and then therefore you are now stuck up. So if it is in a mixture, available in a mixture where the boiling points are very close to each other, you can't heat it up, you cannot take it to vacuum, then you are stuck up. Okay, and then therefore you have no other possibility but other than using extraction. Right. So let me talk about what exactly happens in extraction. Okay. So before we do that, we may want to talk about, again, this will not make much sense today, but I think we have to get started somewhere, or maybe it will make sense after some 15-20 minutes. So let us talk about the notations in extraction. Okay. And take it from me, this is tricky, because there can be different notations that is often used in extraction. So if there are any unanswered questions, kindly take note of them, and please feel free to grab me by my neck later that, sir, you have not answered this question. Because in a class you never let me go, here I might skip. So we will come back to it. So first thing is, these three components are marked with A, B, and C, which we already understand. And these alphabets also stand for their masses or mass flow rates. So why mass or mass flow rate? Obviously, you can have either a batch extractor or a continuous extractor. So also remember this picture, this is going to be the most significant picture. Let me this is going to be the if you understand this picture, if you can remember this picture, you can somehow mark this picture, you understand extraction 50% straight away. Only important thing you may need to remember, it's a important disclaimer, let me tell you, extraction does not involve, or if any one of the phases, particularly if your solute is a solid, right, and you still use a liquid to extract it or sort of take it out from somewhere, it will not be considered as extraction. Please remember, don't make this mistake. Extraction never involves any form of solute, right? It will be considered as leaching. E is B plus C, Yes. Thanks for correcting Chetan. Yeah. Disclaimer is, okay, I'll write it down. Yes, sir. So if you have a process which is very similar to the concept that we have discussed, right? So you have a chemical C which is with A, right? And you use a liquid solvent, let's say B, to extract out or to eject out C from A, right? But remember, C is a solid. That process will not be extraction. That process will become leaching. I will give you an example of roughly the same technique where A and C are solids. Why should I give an example? Can any one of you give an example? Of course, knowing, fully knowing that this is not extraction. Anyone? Salt and pepper? Not exactly, not a great example. There is a far, far, far better example. Alloys, much simpler. Sand and sugar, no. Far simpler practical example. You typically do not mix sand and sugar, Madhuri, right? Here is it. Making of tea. Tea bag or no tea bag. So how do you make tea? And Ujjwal, you were talking about high temperature. Of course, this does not work at room temperature. You typically would like to have high temperature. So what is tea? Tea, you have the chemical, whatever is mixed. No sugar, please. No sugar, please. Tea does not, making of tea does not involve the addition of milk and sugar. First, you can have raw tea also. So tea, either if it is in a tea bag where you have flakes, or if you use the chai ka patti. So it's the tea leaves, dried tea leaves, which contain the chemical, the so-called chemical that makes tea. Now what you do, you take them, right? And then you simply pour some hot water. So the chemical, now the so-called tea, now leaves the tea bag, not the tea bag, now leaves the tea leaves and comes to the water phase, making tea. Isn't it very similar? Isn't it very similar to what we have been discussing? So one can, in a loose way, mention that your A here is the tea leaf, right? C is your so-called tea, and B, which is the water, is the example which is not a correct example, which is not extraction. Is the example clear to all? But remember, this is not extraction, because the name of the technique is not extraction, it's liquid extraction. So please remember, if there is any extraction like process, what are the two solids? The tea leaves and the chemical of tea, the so-called tea, the so-called chemical that makes tea. They are in the solid form, right? When you are taking the tea leaves, there is no liquid. Isn't it, Varun? That's what I told. An analog here is A is the tea leaves, dried tea leaves. C is the tea, so-called tea, and B is the hot water. Am I clear? Don't get too confused. If it is difficult, we will just leave it out here. Then, of course, one can come with another question, related question, and as you remember, as you know that I always encourage you in thinking. A related question is, why don't we get instant tea, right? Like instant coffee. That can be another question. So why doesn't somebody separate out the chemical or the tea from the tea leaves and just sell that as a powder? So just like an instant coffee, like Nescafe, what you have, why can't you simply mix it with hot water and make tea? That can be one question. So instead of going into this details, which is related to, which is a very valid question in the area of food science, it turns out that if this so-called tea is separated from the tea leaves, right, it contaminates in presence of atmospheric air and it becomes poisonous or something. There is some degradation and therefore it is not done. In fact, if you ever wondered why the coffee in our Nesky shop in Nalanda or close to the department is 5 rupees or 7 rupees, and if you walk into CCD, it's at least 40 rupees, the answer is right in front of your eyes, right? So if you go to CCD, what you will actually find, the coffee machine they have, which we all term as machine, kuch hai, something is happening, is nothing but where leaching is happening or decoxification is happening, which I will teach when I talk about leaching. Let's not get into that because I'm drifting a little too much away. So I will stop this discussion on this particular topic now and come back to what we were discussing. So please remember, because this is one problem I encounter repeatedly in Grand Viva every year. A lot of people saying, when I ask what is the method by which if you're making of tea from a tea bag, people say it's extraction. Please remember that if there is any solid component involved, the method is not extraction. It becomes leaching. Okay. So this is not relevant to the notations we were using. So maybe we can do away with this. And what we have, so these are the notations. So A, B, C, and then we have E is the mass of the extract. R is the mass of right. So of course we do understand the simple mass balance. Okay. I will just take a 5-minute break, please. Just give me that 5 minutes. So welcome back. Sorry, I had an important phone call which I could not get. Right. So let us get back to the discussion. Let's leave the leaching part later because we have a separate topic or chapter on leaching, which will come after maybe 2 months, so that we can have a detailed discussion. So there is another way of, so first thing is these are the notations. So this is the simple figure that you have for those notations. And you also use X and Y. So X is the weight fraction of C in the solvent lean phase. Sorry, this is the extract. Okay. Now there is some. So this is very simple actually. So we also have the. It's essentially the weight fraction of C, which is importantly, X and Y are both in the liquid phase here. So important thing to note is X and Y are here. Unlike distillation, where X is in the liquid phase and Y is in the vapor phase. So coming to the notations or whatever we were discussing, let us just, we were talking about the difference between extraction and distillation. So let's add a point over there. So we understand that distillation works based on difference in boiling point components. Extraction works difference in solubility of C in two components. Is it clear now? It should be clear. And therefore, this operates or works based on the concept of VLE. I hope all of you have done chemical engineering thermodynamics, and therefore you all know what is VLE. It is the concept of vapor liquid equilibrium. What does extraction work on? Extraction works on the concept of what is known as liquid liquid equilibrium or the fluid phase equilibrium. This should be clear to all. This is, I mean, today is the first class, so I really cannot, even if I desire, I really cannot make it that exciting. But I can assure you that slowly we will we will all start enjoying these courses. There is so much to learn. So so typically one also writes YE and XR. Any comment that you may want to make or any interrelation between YE and XR that is obvious from this single stage extractor? The obvious relation is they are in equilibrium, right? Is that clear to all? Everybody understands what we are when we are talking about YE and XR are in equilibrium. Is it clear to all? Others, please. I'm just seeing few of you responding. This is not a very good sign. Yes, Anshuman. This is how it works. So, I mean, not exactly the working principle. You would also have to sort of ensure or give enough time of mixing and settling within the container. There is no immediate equation over there. You need to give enough time for mixing and settling in the container, right? Which is adequate enough for the phase B, for C to diffuse from A to C. This is where diffusion comes in. So again, another point I always emphasize. So many times I ask people, give some examples of mass transfer operations. So typical examples are like evaporation, like distillation, extraction, leaching, adsorption. These are all drying. These are all mass transfer operations. But please remember, diffusion is not a mass transfer operation or a separation process. Diffusion happens everywhere, right? Even in distillation, there is diffusion. Even in extraction, there is diffusion. So where is diffusion in extraction? How is C leaving A, right, and going to B? This is by the process of diffusion. So essentially, C diffuses out of A into B because what is the driving force for the diffusion? The solubility is the driving force, which you can correlate to the chemical potentials, right? So, and also it is important to understand that how long this diffusion will be sustained. This diffusion will be sustained till the saturation is attained at max. The saturation is attained in B, right? So it's complicated. Let's not get into the all that right at the beginning on the first day itself. But this is how it works. So this is where diffusion is. And again, I'm coming back to Ujjwal's question. So why not high temperature? Of course, there is another advantage. If you increase the temperature, the diffusivity also increases. So you might actually have faster separation, but there are other issues which I will talk about. Why you typically avoid high temperature. And okay, so when I will talk about it when it comes. So this is the general or the easiest notations that one uses in extraction, which is like in, so when you are calculated the XR and YE, this is the fraction of C, right, in the extract and the raffinate. So what exactly is, so you can that way calculate the 4 fractions. So you can have a YF, you can have an XS, you can have YE, and you can have XR. So you all understand what is this? This is fraction of C in feet, which is the amount of C in feet. XS is fraction of C solvent. This should be C divided by B if it is a pure solvent. And what would be its ideal value? Its ideal value should be 0. So what is YE? It is the amount of C in the extract divided by C in the extract, A in the extract, plus B in the extract. I am keeping A because in one of the earlier earlier time we talked that there can be trace amount of A also, this power point. Yeah. So bad habit I have, I don't save. Okay. So we lost some text. I have some problem, Ishan, with the whiteboard. There is some problem I had. As I told, I'm not very tech savvy. I'm getting old with every passing year, and I have some problems. So I prefer to use the PowerPoint. Thanks for your suggestion. I mean, who is making an angry face at Ishan? Ujjwal, relax. Okay. So all of you understand that y xs should be equal to 0. Is that clear? So let me just check. So this x and y are all fractions of C. Is this clear to all? Y xs is 0. Right? Because it's a pure solvent. So therefore there is no C. So this is the easiest way you can use the notations. However, there are some special type of notations that are also used in extraction, and in some problems we will see that they are used. That is the symbol N, which is weight fraction this is again, I would request all of you to just note down. Today it is very difficult for you to understand what it means. So this is a very strange notation that one uses, a symbol N, which is the weight fraction on a B-free basis. Very surprising. You do not consider the solute, so you do not consider the solvent. So you can have NF. So I repeat, it is the weight fraction on a B-free basis. So N you can calculate for all the 4 streams. In fact, here there will be a correction, 3 streams, and I'll leave it like that. Streams. And so what are the streams? So one can calculate NF, NS, NE, and NR. And can anyone point out what this means? So N turns out for any stream. If you have difficulty, just hang on, I will explain. For any stream, N equal to weight fraction, sorry, I made a mistake, weight fraction of B on a B-free basis. That's very interesting. So this is N for any stream is B divided by A plus C, right? So I would like to repeat it again. You understand, because this may not be tomorrow or in the next class, but in one of the subsequent classes, this is going to be a very, very important notation. It comes with its own advantages also, which we will talk. So there is a unique notation, which is N, which is the weight fraction of B on a B-free basis. So let me write it neatly. Weight fraction of B on a B-free basis, right? So what is weight fraction of B on a B-free basis? So what is the difference between N and X, let's say? Firstly, X was the weight fraction these are notations and we will learn it. There is no problem. X or Y or X, were the weight fractions of C, right? Now, one can also ask me one small thing I forgot to mention, not forgot to mention, I did not discuss, but it is good that we discuss. See, when I say that we write XR and YE, right? I say it is the convention that the weight fraction of C in the extract we write with Y, and in the raffinate we write with X, right? So these are weight fraction of C, or I will repeat, weight fraction of C in liquid. So there is no vapor or liquid like distillation which would have allowed an obvious distinction between X and Y. This is the first thing you may want to understand, right? Or in other words, one can say, sir, what is the problem if we write XC and XR? Theoretically, if you can do your bookkeeping well, there is no problem, or logically, because both are in the liquid phase. However, it is more of extraction pedagogy, or to draw an analog with distillation, analogy with distillation, or the notations in distillation. The extract phase, the fraction of C in the extract phase is mentioned as Y. So this we agree. There is nothing to understand. This we just agree. This is a piece of information. I am telling you or teaching you that this is what is done, and you are agreeing. So this we agree. Once we agree to this, then comes immediate question that why do we choose? This is the question. Is the question clear to all? As you know that I often won't ask the question also, I will get the question out from the class. The question is, why the fraction of C in the feed we are writing with Y, and that in the solvent we are writing with X? This is the question. This is the question. Who has told us? See, when we say that we are using Y for extract and X for raffinate, that is okay. It's a logical way of representing that we have designed and we are using it. This we all agree. So if we agree to that, why we write an Y over here and an X over here becomes clear, right? But then comes the question that why are we using? I'll take a minute to get this cleared. Otherwise, a lot of students suffer with these notations in extraction. So are you noticing that we are using YF and XS? I'm asking to the whole class. Have you noticed that we are using YF and XS? Why this distinction? Well, to be very honest, This is, well, is that totally wrong? Because if it is solvent rich, then one should have used YS. Let me see. I hope I'm telling you the correct thing. Okay. So this also we will talk when we solve some problems. I think by next class we will be in a position to solve our first problem, and that will make this concept very clear. So kindly carry this in your mind. The notations about feed and solvent. And I also have a little bit of doubt. So this I need to cross check once whether this I have written correctly or not. I will confirm. If there is a mistake, I will confirm. I don't have Treble's book with me in my office, so I will just confirm. It's most likely I'm right, but I will just confirm. And see, I'm also teaching mass transfer after a year, so I'm a little rusted today. I will also pick up by the next class. Anyway, now coming back to what we were discussing, this unique notation of n. So is it making some sense? It's a complicated concept, let me tell you. So n is sort of an artificial number that you are calculating with respect to every stream. It is not the directly something very similar to x or y, because x or y is the proper weight fraction of C in any stream. But n is defined as a very unique way, or it's defined in a very unique way. It is the weight fraction of B on a B-free basis. Now, why this happens, we will again see later. We cannot really tell you straight away why or under what conditions or for what type of situations this is very, very handy for problem solving, right? So what is n? N is actually the value of B divided by A plus C in any stream. So you can have BF, right, divided by AF and CF. You can have BS in the solvent divided by AS plus CS. You can have BE, you can calculate NE, which is going to be, let me write it. For example, NE is going to be BE divided by AE plus CE, and NR is going to be BR divided by AR plus CR. And what is going to be the likely value of NS and NF? So the likely value of NF is going to be 0 and NS is going to be infinity. Is it clear? Because, so Anshuman says yes, but I would request the class to take a very careful look of why NS is infinity. Because NS is the fraction of B or B-free fraction of B in the solvent stream. And if it is a pure solvent, right? If it is a pure solvent, you have no A plus C. So your denominator in case of the solvent stream is 0. And therefore, NS is in most cases infinity, right? And remember, if you have a number that is infinity, you can't locate it in a graph paper. Similarly, what about NF? Feed is generally pure A plus C. Feed is A plus C. Ideally, it should be free from B, right? And therefore, what is the value of B in feed? BF is going to be 0. Therefore, NF in most cases is 0. Is this clear? Is these two numbers clear? So if this part is clear, then you have understood the B-free weight fraction. Take a minute to convince yourself. You might feel a little bored why I am spending so much time on such trivial things, but this will be very important later. Okay, so one set of notation is just ABCEF, not EF. A, B, C, E, R, right? And we simply use X and Y, which is the weight fraction of C, right? The second set of notation is the notation or the weight fraction of B on a B-free basis. So A, B, C, E, and R remains. Along with that, so essentially you would understand that A, B, C, E, and R collectively will give you the mass balance. So whenever you are writing this X, Y type of thing, you are essentially looking at the component balance. So one can do the component balance with the weight fractions of C also. One can also do the component balance with N. More important thing is that when you are defining N, it is on a B-free basis. So that is very interesting. And since it is on a B-free basis, it comes with its own problem, because N for a pure solvent is going to be infinity. And that's the other one is not a problem. It's more of an observation. N for the feed is going to be 0 in almost all cases. So I'm asking one last time, is it clear to all this concept of N? It is more of an understanding rather than a concept. Okay, good. So if we understand that, then we also have another notation, which is, so X and Y we understand, weight fraction of C. In raffinate. We can have another notation, which is X dash. So X dash is so can anybody tell me what is X dash? Mole ratio? No. Anshuman, carefully. It's very similar to N actually. Very good, Chaitanya. Very, very good. So X dash and Y dash are weight fraction of C on a C-free basis. So Asawari has said solute-free basis, but please also mention it's the weight fraction of C on a C-free basis. Yeah, mass fraction of the solute on a solute-free basis. This is interesting actually, if not tricky. In the raffinate, right? And one last set of notations. You can also have capital X and capital Y, which are weight fraction. This is one note I would like all of you to sort of keep, and we will not spend too much time on this again today, right? And we will revert back to these concepts what we talked when subsequently different types of problems we handle. Weight fraction of C on a B-free basis. And this is also the same thing. Of course, capital X would be raffinate. Weight fraction of C on a B-free extract. So these are the general notations. So let me sort of write down a quick summary. A, B, C, E, and R are the, or one can also have F and S. These are the streamwise flow rates. So rather it's more accurate to say F, S, E and R are the streamwise flow rates. Then comes the different notations. Sort of write it here. So one is the most common notation, that is the weight fraction of C, proper weight fraction of C, and that is represented in terms of X and Y, small x and small y. The second one, so this is set one can say. And you have to excuse me and give me some time before we can start understanding the proper utility of these notations. I will not be able to convince you about the utility of these notations today itself. The second set of notation is the weight fraction of C again, right? Well, Ujjwal, not exactly. These are the mole fractions, actually the fractions. These are the fractions. See, because when you have a three-component mixture, right, your actual weight fraction, these are weight ratios, but it is sort of looking into the fraction of B. What is weight ratio? So when you calculate, let's say C, when you are calculating X, for example, XR, what is XR? It is the C in the raffinate divided by A in the raffinate plus B in the raffinate plus C in the raffinate, right? That's what you are calculating. Therefore, it's a weight fraction. Of course, weight fraction is nothing but the ratio of the flow rates of the total masses, right? And then we understand that since it's a raffinate, so let me just write it down. There is every reason for people to get confused. So XR, when you are calculating, is actually this number. And then we do understand that in a properly executed extraction, or when your choice of solvent is proper, that means the solubility between A and C, sorry, the solubility between A and B is very poor, then of course you should be knowing, you should be understanding from your knowledge that this is going to be likely to be 0. This all of you understand? So this is clear. Let me check it. I mean, it's a good point you have raised. What you have said, I do not fully agree, but let me revise the whole thing in that pretext. So is this clear, for example, to all of you? Others, please. Is this clear to all? Now, when we are now talking about X dash R, what are we talking? We are actually talking about this entity. I won't say it's confusing, but you have to just be a little careful as you are beginners. So X dash R is CR, C in the raffinate, divided by AR, because it's on a C-free basis. Now, what is XR? XR is CR plus AR. This is on a B-free basis. It turns out that in case there is no solvent in the raffinate, capital XR and small xr are going to be same, right? However, if you talk about YE, yeah, we are sort of neglecting. That's exactly what I told. And please notice, Ishan, I have used an approximate equal to 0. Otherwise, if there is trace B, the values in the second decimal of capital XR and small xr will be different. Correct. Right? We are, as of now, we are assuming that there is perfect separation, but when we start working on a problem, we will find there is always trace amount of B. Right? Now this is turning out to be a good discussion and I don't have space. However, so this is clear to all. As per Ishan's statement, if we assume that there is no B in the raffinate, is it clear to all that essentially small xr let's create some space. Great. However, YE is going to be CE divided by AE plus BE plus CE. Again, we assume AE is going to be very, very less here. And YE is going to be CE divided by AE plus CE. And if we say AE is negligible, this will tend towards 1, while this will not tend towards 1. So there is the difference. So Ujjwal, as you were telling about, these are the same things as the weight ratio. Here shows up the difference when you calculate on a B-free basis or on a C-free basis. Some values might remain same, some values might be different. So is this clear? For a reasonably ideal extraction unit, your small xr and capital XR will roughly give you the same values, right? Because capital XR is on a B-free basis and the extract ideally should be lean in B. Okay? Sorry, the raffinate should be lean in B. Okay? However, when you are calculating the Y, so YE you have some value, but when you are calculating YE, the BE is a significant factor in the extract phase because it's B rich. So BE is a significant factor in the extract phase. And now when you are defining YE, this BE itself is missing. So these values or the numbers will be significantly different. So kindly keep note of this discussion. So we can have X and Y. We can have X dash and Y dash on a C-free basis, or we can calculate the fractions capital X and capital Y on a B-free basis. And so these are, so whenever we are writing, what is important to note that all these three stuff that are ticked, these are the fractions of C. These are all fractions of C. N is different or stands out that way as this is fraction of B. This is fraction of B. Typically, why I have subgrouped them as 3A and 3B is because of the fact that typically N and capital XY are generally used in unison. They are used together for solving problems. X dash Y dash is used in one specific cases where things are completely immiscible, which I will give an example subsequently. It will take at least 3 weeks before we reach that stage. And the most common one, what we will get started from the next class is, of course, X and Y. Okay, so these are the notations. I'm sorry, it sounds a little heavy maybe today, but today is a double lecture and we really do not afford to sort of leave everything for the next class. So something or the other has to be taken. Now, of course, then we understand that the process of extraction, we just left with 10 minutes. I did not know how the class comes to an end so fast. So in extraction, we are handling three liquids, or rather three components. So since it's an equilibrium process, we also need a phase diagram. In order to proceed, we need a phase diagram. So how do you handle three components? So let us quickly revisit our knowledge about the phase diagram. For a one component system, what is the typical phase diagram we drew? Right? So this is the typical phase diagram we drew for one component system. Since there was only one component, we could simultaneously vary both the pressure and temperature. And what phase diagram is this? Of what, which material? This phase diagram everybody remembers? And then immediate question, is it a typical single component phase diagram or something special about this particular phase diagram? Harshal, how do you know it's water? Because I have not written. Jishnu, yes, very good. Anyone, how do you know it's water? The slope of which line, Asarya? Negative gradient between the solid liquid curve, solid liquid line, SL, very good. And how do you justify this? How do you justify this? I have taught in your CPC. So how do you justify this? I have taught. So let me also see what is the retention. Density is one indirect way. There is a more direct way. Of course, ice floats on water is an indirect validation of the fact that the density of the liquid, the density of the solid phase is lower than melting point decreases with increase in pressure. Very good, Madhuri. Regulation, what I taught you. If you take two blocks of ice, press one against the other, they convert into a monolith. Regulation. Right? I have taught. I remember. I still remember. And this is, I have taught in CPC. And this is the only time when I was teaching regulation to the present second years in an online mode. That's the only time I really felt that online class is not that bad, because after I gave the example, many of the students after the class took out two blocks of ice from the refrigerator in their home, pressed them together, and sent me pics that indeed they are forming a monolith. So what exactly is happening? What is happening is, as you apply pressure, right? As you apply pressure, as pressure increases, water at a particular temperature, which was at a solid phase, solid state, ice, water, ice at a particular temperature, which was in the solid state, now transforms into the liquid phase. So when you are pressing two blocks of ice, upon application of pressure, here it becomes liquid. So the interface between the two ice blocks disappear, right? And now when you withdraw the pressure, it traverses back in this way to the solid phase. But now the layer of water in between the two blocks freezes and there is no interface. Therefore, two blocks of ice two blocks of ice join up, which is called regulation, is the most convincing proof that the line, SL line, has a negative slope. This I should not ask, is it clear to all of you? It should be clear to all of you. Is it clear to all of you? This is the most direct evidence. So those of you who are again giving the example of ice floats on water, that's an indirect evidence. Why? Because the idea is that as you apply pressure, right? As you apply pressure, the molecules come closer to each other, right? So as you apply pressure, the molecules come closer to each other. And in that way, as the molecules come closer to each other, its density increases. Now, as you apply pressure, you know that density of liquid is higher. So how is that possible? So as you apply pressure, this straight line must be going to the liquid phase, which is not possible for a regular material where the SL curve is like this. So you apply pressure, it remains in the solid state. So for water, what happens is this slope is negative, and therefore upon application of pressure, it must be going into the liquid phase. This is an indirect evidence that the SL curve is negative for water. This is a more direct evidence. What you still cannot explain, please also remember this, this is also important. What you still cannot explain from this phase diagram is why water has highest density at 4 degrees centigrade. Again, some people make this mistake that you can explain this from the negative slope. No, you cannot explain. That you essentially depends on the properties of the hydrogen bond, the bond strength, or the strength of the interaction. Hydrogen bond is not a proper bond, of course. The strength of the polar interaction is maximum at 4 degrees centigrade. So this is what is a typical one component phase diagram. Now, what about a two component phase diagram? Two component phase diagram is again two miscible liquids. If we talk about, this is the most common form of a two component phase diagram, and again this is X and Y, and this is T. But in order to accommodate for two components over here, you have to make, so the moment you have two components, you essentially talk about X or Y, which is the, what is X or Y? It is the fraction of the more volatile component in the liquid and the vapor state. Traditionally, if you are talking about a benzene toluene system, X or Y will always refer to the fraction of the more volatile component. So that if you define the more volatile component, you anyway have two components. So the second component, composition of the second component is also 1 minus X or 1 minus Y. It gets automatically defined. Fraction of the more volatile. And the moment you bring in, so one of the axis is consumed in the composition, one of the axis is consumed in temperature. So you can have this type of a diagram only at constant pressure. Right? I will stop. It is 10 o'clock, and more than you, I have an immediately instability class right now. So I will pick up from here next Monday, and what we will learn is how to represent a three component phase diagram. Thank you very much for your time, and I'll see you in a week's time. Thank you.